Alright guys, let's get started. Welcome to the July meetup. So there's no announcement, so let's just jump right into the main presentation. We have Ryan here from Aerospike. He's going to talk about the interesting world of ad tech, especially real-time bidding, and what are some of the lessons enterprise can pick up from there. Cool. Ryan? Hi. Thanks for coming out today. How many of you know about real-time bidding and advertising? Okay, small handful. I'll go over that quickly then for those of you not fully into it. So my name is Brian Bulkowski. I'm the CTO of a company called Aerospike. So we are one of the new NoSQL fast databases. I'm not going to talk to you today about Hadoop or analytics. I'm going to talk to you about real-time big data, operational big data. So how fast can you go over what sizes and why on the front edge of your application, and what that can mean for the kinds of solutions you build and what's happening in the industry. My background, I was head of Apple Talk protocols at Novell back in the early 90s. I did a lot of work with video servers, real-time delivery of networking throughout the late 90s, early thousands. A company called Liberate through the boom. Many of you know about that. It was a Jim Clark company in the embedded HTML space. And got involved in advertising in about 2007 and really found out the level of scale that these guys were operating at. So got excited about that enough to actually take some of the technology that I was learning to build my own database. So we're a venture-backed company based here in Silicon Valley and Mountain View. We also have offices in Bangalore. We have about 100 customers right now, large-scale big customers, as well as the fact as about 6 weeks ago we open sourced the entire database. So please come and check out the database. It's about 10 times faster than Cassandra, for those of you who use that. Or compared to Redis, it's about the same speed, except it's clustered and uses Flash. So in any case where you'd be using Redis, but really want to already have a built-in clustered layer, that's the kind of space we're in. So what happened in real-time bidding was about like this. In around 2004, and sort of around to 2004 to 2007, what happened in advertising was you could buy, as a brand, space on a web page. It was just like in a magazine, right? So you're in Forbes, you want to buy page number 4, and you put your ad there. Whoever opens the magazine, they can see your ad. And that's where everything was up until about 2007. There was an industry called remnant advertising. And someone said, you know what, those remnant ads, they still get in front of a person, and they're cheap. So instead of saying, hey, look, let's buy on a page, let's try to buy a person. Let's try to put an eyeball in front of you, sir, in the back. I want his eyeball, and I want to buy that. I don't care about the page. And that was the birth of real-time bidding, was trying to get your ad and your impression in front of an individual person. So what happened was Google in particular took their remnant advertising, Yahoo did this also as part of DoubleClick and Right Media, and they started syndicating out and allowing different companies to bid on and fill advertisements that were in Google's system and in Yahoo's system. Several companies showed up, notably AppNexus, some of the other ad networks, and in order to fill this need. So we had data management platforms. They sprung up in order to capture information about people on the internet, buy and sell it, and even buy and sell analytics. So of those, BlueKai is probably one of the most interesting. They're down in Sunnyvale. They recently got bought by Oracle, very nice company, and they buy and sell the analytics. So you can actually you can buy information about a particular audience and who's in that audience, what cookies are in that audience from people in these data management platforms. Within the ad networks and SSPs, that's where you actually had the brands meeting the advertisements and displays. So, and in the exchanges. What happened in North American RTB was, at first, it was fairly small. There were only about 200,000, 300,000 auctions being run every second. So what happened in advertising was they looked at the capital markets because they wanted to have more companies buying and selling advertising and a better reach of these things. So they said, you know what, In the capital markets, in trading stocks, you have basically the buy price and the sell price, right? And when the buy and the sell overlap, then you actually have a trade. Well, those exchanges work at a much slower rate than advertising. That's only happening at tens of thousands of times a second on the public markets these days. And so what the advertising guys said was, they said, this is more ephemeral. This is a URL and a given cookie set, a given a person, and an IP address. We know that about a person. And how are we going to price this thing? Nobody knows how to price it. Is a person we know a lot about, we don't know a lot about? Are they ready to buy something, not ready to buy something? Nobody knows. But let's price it. So what they said, what the ad exchanges said, was they said, let's run an auction and try to figure out what the price of this particular person on this particular website right now, what's the price of that? 0.0001 cents, 0.002, etc. So that's what they did. They started running these auctions. And AppNexus was one of the first companies to do this. And they said, we're going to take the remnant out of these sites and start monetizing it and finding the fair price. So different companies who wanted those brand impressions to reach a broader audience, who weren't getting the audience reach that they wanted, started buying on these exchanges when they saw certain cookies. Each one of the companies bidding on the exchange was using their own math. So for example, there are some search retargeting companies out there. They are looking for search terms because they talk to, once you're on the exchange, you get to start seeing what people's behavior is, what search terms they've used recently. So if you can start doing that and hook into websites where there are search boxes, you can say, hey, if you searched for this, I know about that. I'm going to target you later, retarget you. If you search for shoes, I'm going to show you a shoe ad in a few hours. And they started building up these fairly complex big data models. A lot of the folks in this space are using Hadoop clusters, such as AppNexus. Their Hadoop cluster is probably upwards of 50 petabytes to 100 petabytes. And that is all of the behavior that they have seen since the beginning of their company. So 7 years worth of every single impression that has come through their network. They allow other companies to rent time on those analytics systems in order to run their algorithms. So let's say you believe search retargeting is the way to get better brand impressions, or maybe you're an advertiser and you said, hey, look, Nike, I'm going to get you in front of everyone who has searched for shoes in the last day, and that's what I'm going to sell you as an advertising guy, right? So search retargeting is one way, geographic targeting is another way, hasn't caught on quite as much. And there are companies, one of the great things as CTO is I get to talk to these algorithmic guys and see all the crazy ideas they have, whether you're using fairly complicated k-means metrics based on k-means cluster sets. Everyone's got their own algorithm. So right now, what we're finding in North American real-time bidding is about 1 to 6 billion cookies tracked. Right? These guys can't track people, that's illegal in North America, but you can track a cookie. So they don't have your name, they don't have your phone number, they don't have your address, they don't have your email address, but they do know your cookie, right? They've planted all of these cookies. So what we find is that they're tracking about 6 billion cookies for North America, and they're usually keeping around 1.5K for every cookie. Now some companies I know of, people like Rocket Fuel up in Redwood City, they're actually tracking more information per cookie. Their average is probably closer to 20K per cookie. So everyone's got their own idea, because everyone who's involved in one of these auctions has their own private data. That's one of the reasons one of the ways that you win in one of these bidding situations is having your own data and your own information. So you've got your own analytics, you've got your own real-time data, and you're making decisions on the real-time big data decisions on that operational side. Now, the Facebook exchange is an interesting story. For those of you who don't know it, I'll tell it real quickly. So what happened at Facebook, you remember in the 6 months after they went public, they had a lot of revenue shortfalls. Those revenue shortfalls were because they had plenty of people coming to their site, but they didn't have enough ads. So what do? Well, it turns out these bidding exchanges, there's a lot of advertising, and there's a lot of chances to buy someone. So Facebook said, hey, guess what? If we need more ads coming in, we've got the impressions, we need to hook up to the exchanges. prior to that moment, they said, we're going to do a closed shop. If you want to advertise on Facebook, you've got to advertise on Facebook, and we're going to take all your money. We're going to own the value chain. They realized that even Facebook wasn't big enough to do that. They had to open up Facebook Exchange to get more revenue in. So they called up, Brian O'Kelly at AppNexus has this wonderful story he told at one of his conferences. And he said, the guys at Facebook called them up one day and said, all of those ad impressions you're getting from Google, we're going to double it. We'll give you exactly the same amount of traffic in the front door for advertisements that Google is giving you today. And we want to go live in 6 weeks. So we want to take your exchange from 400,000 auctions a second to 800,000 auctions a second. And we want to do that this fast. Are you ready for it? So these companies are often, their business is expanding and adapting to new traffic, right? New business opportunities. The ability to have a technology stack to be able to adapt to that kind of business requirement, immediately going from 400,000 to 800,000 a second. That's kind of what the internet's all about, right? That's what the cloud is about. You know, just give me some more instances and being able to elastically scale. That's the kind of opportunity that changed AppNexus from a medium-sized company to now the I think 800 employee, on track to IPO kind of company. So the time limits within real-time bidding are as follows. What happened in 2004, 2005 was that content sites like Washington Post, they were starting to put a lot of ads on their site. They were starting to see their pages slow down, right? And so they finally said, hey, look, if you're going to place an ad on our site, you have to get that ad to a customer within 150 milliseconds. And that's based on human perception. That's the limit at which you start feeling snappy, is something happens and bam, within about 1/8 of a second, something happens. So they said, this is the limits of user perception. We want to see the ad delivered to any user in the United States in 150 milliseconds. Some websites went with 100 millisecond SLA. This became the backbone of why real-time bidding happens at the speed it does. Because, well, North America is 79 to 90 milliseconds wide. So if you're going to get an ad to a particular user, you have to start the process of delivering it within a certain period of time, which has driven the auction to usually at a 30 millisecond limit, and thus a 5 millisecond close for the auction, which typically happens among currently about 100 to 150 companies, external companies that have ads that are trying to bid. So that's what's happening in real-time bidding. Here's the tech stack that has evolved to make this happen. First of all, big data. There's a huge amount of analytics back there. The guys at AppNexus, the old CTO, Mike Nolan, has this great talk that he's given where he said, you know what? We've got 15 databases back there because we've got so many kinds of queries. We've got, some new hotshot data scientist comes in, he says, I know the path to greater revenue. We need to do this kind of analysis. We need to do a 3-layer graph, right? And they say, okay, fine, guy, go provision some servers, do your analysis, and we'll see if there's actually signal there and you can make money in the auctions. So there's all kinds of databases that have back there based on query type. Those are all batch analytics. If they go down for an hour or two, it's okay. What he says on the front side, though, the real-time portion of it, is you can only have one database. It has to be an in-memory database because you can't be beholden to particular access patterns and particular caches. In-memory is the way to go. Highly sharded. And since we're going to work at a rate of 2 to 3 million operations per second fetching that cookie data, it better be pretty fast because we can't spend all of our money on servers. So this is the kind of system that they used, one where you've got an app server, and one way I think about it is this is how to separate out compute and data. It's really good in a lot of the architectures I've worked with to have a 2-layer architecture because you have memory or storage and then you have compute. If you've got 2 layers, you probably have the right number of layers for a given architecture. The app server has become the compute layer. That's where you do your computation, and there's a storage layer underneath it. And I've seen company after company where sometimes I need to store that storage layer, scale the storage layer. I need to double the amount of data per cookie. I need to increase the amount of computation a factor of 3 because I've got a new algorithm there. I want to scale those 2 things separately. So that becomes the app server where your computation is, and your database where the actual data layer is. So here's what enterprises have learned from this. Because this all started in real-time bidding and advertising, and has been a real revolution that is starting to reach out through different parts of the rest of the computer industry. I don't know of almost any other industry that is working at the speed that advertising has achieved over the last few years, and that kind of tech stack. So, for example, financial services. At Aerospike, we now have a signed POC that we're working on for what's called intraday positions. What that is I go to my broker and I want to know what's in my account. Well, with the rise of mobile, with faster trading, with people needing to know or wanting to know what's in their account right now, fast portfolio rebalances are a part of that. These companies banks want to have a asset-compliant position of record database that is much faster than what they've had before. These guys have often used DB2 or Sybase, very strong databases, as part of their transaction chain. You know what? They still have them. Because for compliance reasons, you still have to be able to trade securely, but you use reconciliation, right? If there's a case where you have a certain kind of hardware failure and that front-edge database says, you know what, or if you work in financial services, you know that XA transaction chains for these complex cases often have 10 steps of processing. Did this clear? Did that clear? Did I get a signature on this? What was my counterparty risk? Blah, blah, blah. You have all these steps through the transaction chain, and they allow end-of-day reconciliation. So this thing shuts down, the trading system shuts down, at which point they can do all the reconciliation at the end of the day. All of that stuff still exists, but I want to see what's in my account at a much higher rate than ever before. These guys are now reaching to internet technologies in order to do that. A lot less analytics, right? The trading guys are still using the kind of big data analytics, but these guys are now wanting 1 through 5 terabytes on this front-edge operational store in order to satisfy the kind of UI that they're now proposing. Okay, social media. So I had a chance to go to China and talk to all the major social networks in China. And they're, for some reason, I don't know, maybe it's the fact that I'm American, they were a little more open than, let's say, trying to go to Facebook and talk to them about the tech stacks that they're using. But Facebook's actually not that different, right? They're still using highly sharded systems. Facebook standardized on using MySQL as their core data store for that front edge. But it's still highly sharded, revised replication. So what the social media guys in China really started focusing on was using Redis and sharding Redis. So what they said was, you know what, we know we need in-memory for all the reasons I said. It's hard to predict. Which user is most important? Are a particular set of friends going to get hot for a bit and then not hot? Really hard to cache all this stuff. So they use a huge amount of sharded Redis. They had to build their own sharding system. However, they also realized they couldn't deal with RAM. Or they started with RAM, but RAM just became too expensive. They would have the last 10 days of social media, and then as the site got bigger, they had only 7. So what happened in China was Redis has been modified to support SSDs, which are inside these companies. However, none of those companies have turned and contributed those back to the open source pools. Why should they? That just helps the other guy and helps their competitors. So they've taken the open source project of Redis, modified it for SSDs, and then not contributed it back. But that is basically the architecture that they've used. Now let me call out one interesting thing, which is the data abstraction layer. The guys I talked to had a pretty interesting strategy, and I've been recommending it for a lot of front-edge applications, which is a strong domain-specific query layer. So one of the problems with databases of the past and relational systems is, as an application guy, you can write any SQL you wanted. You didn't have to, the old days, you had to actually go through a DBA and register your queries and go through query planning and all of that kind of stuff. And in the fast-moving agile environment that we have today, you just write the SQL query you want, you put it up and test your app. So what these guys at, I think it was Weibo that I talked to, they said, you know what, the big win for us was separating out the engineers who are scalability engineers from the application development engineers. So what happens is they create a domain-specific layer that is things like get list of friends, send message to friends, store user-generated picture. And so the application guys go crazy with this, and they're building more and more interfaces. It becomes a negotiation point in their company. to be able to go to the scalability guys and say, hey, I need a new feature. Instead of just coding up a query and running with it, they have to go to the scalability team and negotiate that new domain-specific API. And they said that was really one of the keys for them, was that the scalability guys can work with that API and can find clever ways. They can institute a new database. Well, this kind of user gets this database. This kind of user goes in that database. Fast-moving users, slow-moving users, users with long lists and short lists. They can do their business as scalability engineers, and the UX guys can do what they need to do as well. These social networks, really excellent engineering within them, and I recommend some of the approaches that they have for front-edge big data. Let's talk about the travel industry. Anyone here in the travel industry? Doing technical work? Yeah, a lot of that's done on the East Coast still. So if you know travel, and we all buy tickets of all kinds, you know that they've done dynamic pricing a lot earlier than a lot of folks. So the kind of real-time bidding, dynamic pricing of advertising, was also pioneered within travel. They have big data systems on the backside doing all kinds of prediction of routes and fullness of airplanes, trying to optimize all of these things, right? On the other hand, so a particular company, let's say United, it owns a seat on a plane, and it's trying to price that. Well, but I buy that through a travel website. Well, the travel website, they can't go to United every time there's a page hit and say, what's the price on that? Because those guys are kind of old school, and their infrastructure isn't really fast enough to handle the kind of load of what if Travelocity and all of these guys are continually checking what's the price. And so in that business, they've tried to, the companies that own the tickets and are doing the pricing have created caching layers, but they even demand that a company like Travelocity pays for every API call to try to find the current price of one of these tickets. So that causes people like Travelocity to build another large caching layer. What does that mean? It means when you go to a website and say, okay, I got my seat, it says only 2 left, and then you say buy it, it might come back and say that seat's already sold. That's essentially, in database terms, a consistency problem. Someone else bought my seat when I was told there was already a seat, right? That's a really poor user experience. Everyone hates that. So these guys in travel, now that there are databases like this, are saying, well, heck, we don't need caching layers anymore. We can present a better user experience, a richer user experience, better pricing, sharper pricing, faster moving pricing by using the kind of technologies that ag tech invented. QoS and real-time billing for telcos. Interesting use case. So I'm sure a lot of you are in networking or have networking backgrounds. I certainly do. You would never make a database call in the middle of a router, right? That's crazy. You see a packet come through, you do deep packet inspection, you look at it, and oh look, it's an HTTP packet, it's got a header. Am I going to figure out my routing destination based on a database call? I mean, that's crazy. And yet, what I found is a lot of telcos are interested in adding this. Right now, it's the equipment suppliers. The equipment suppliers want to start having the capability within their usually mobile routers of being able to, on a user-by-user basis, change QoS and change routes. Now, I don't know exactly why they want to do this. I didn't ask and they didn't say. I'll leave that to your imagination. But that's what's happening. They're trying to do essentially personalized routing. They're not doing QoS through RTSP or one of the old routing protocols. They're trying to do it based on user profile, how much you paid, do they have a special deal with Netflix or something like that. I don't know exactly why they're doing it. But the good news is these kinds of in-memory databases that I'm talking about are actually capable in a routing loop of satisfying this kind of database lookup. You can go out and do a lookup in 100 microseconds, which is a reasonable thing as part of a routing loop, and you can do it at 200, 300,000 transactions per second for every single server. So you can start doing a lookup on every single packet forwarded within, say, a given mobile metro, and actually pull these things off. And telcos are starting to do that now, essentially using the same kind of internet technologies. Now, what did they put in the profile? That's offline big data. How did they decide? They're going to do a bunch of, say, graph analysis that's been used a lot in telcos to figure out, hey, if I have slow data, am I going to leave Verizon for AT&T? They might decide to improve your data and improve your latency simply because they think you're at risk of churn, right? Those old churn systems and graph analysis that they've done for the last 4 or 5 years, they're now trying to use that data on the front edge of their router. So some pretty innovative uses. Let's cover one more interesting use case, which is retail. In some sense, this is closer to advertising, but I ran a meetup, I think it was now 4 or 5 months ago, with some guys who were involved in some of the Walmart work. Now, as many of you know, Cosmix, a company down in Mountain View, got bought as Walmart Labs, what was it, about a year and a half ago. And Walmart Labs paid what seemed like an exorbitant sum. I think it was $450 million for Cosmix, which had no product. Well, they bought a lot of data scientists. That's what really happened. And the Cosmix guys became Walmart Labs, and the rumor that I heard is that they contributed $1.2 billion to Walmart's bottom line in the first year of operations. What did they do? They used the same big data techniques that we're talking about in advertising. They do things, simple things. I don't know, I mean, they're all trade secrets. I have some friends over there, but I don't know what they do. But imagine this one. Imagine this kind of retail algorithm. Let's say you're at Walmart, you can discount. You're Walmart. You can discount like crazy to get business, but every time you discount, it costs you money. You don't want to discount. So when do I offer a discount? Well, if I know that this particular user has bought something at Walmart that was cheaper on Amazon when they bought it, you know what? They might not be price sensitive. People fall into psychographies, or even within buying patterns, and you can perhaps tell whether they're price sensitive or not price sensitive using some very simple algorithms and filters. If they are not price sensitive, don't offer them a discount. Offer them a cross-sell. Offer them another, say, hey, look, your friends have bought it somewhere else. Use something else besides a discount. Only discount for the people who are actually price sensitive. And then you can still do real-time pricing analysis. You can go and look at the price on Amazon and figure out if your price is already below Amazon or another retailer, don't discount. You've already got the cheaper price, right? So these are the kinds of algorithms retailers are using now in real time. You're doing the background analysis to figure out if you're price sensitive, what kind of audience you're into, and then on the front edge of your application, do you offer a deal? Do you offer what's called 360-degree customer view of audience? What are you actually doing moment by moment to your customers and offering them both a richer experience, but also more, just the kind of experience that they want. So these things are happening in retail right now. I've talked to people at Target, at Best Buy, and a bunch of different folks. And they're all using, the successful ones are using these new internet techniques. Some are still using a lot of SQL, right? And honestly, the people I talk to doing that are kind of struggling. That's the kind of analysis or the kind of front-end application that's not really allowing them the kind of richness that some of the other guys are using. So sort of what's the takeaway here? The new architecture that I'm seeing is this one where compute is in the app server, the operational database, the OLTP system is an in-memory NoSQL system, and then you've got the kind of batch big data analytics that we're all now kind of familiar with. So how does this change from the quote old architecture, right, just to say around the year 2000? What we used to have on the front edge was we still had an app server, but we used to push down queries a lot more. Queries used to be a bit richer than they used to be. So less of the CPU was in the app server. You would actually have databases running hotter at CPUs. And then you would have this three-part tier. You would have a cache, because databases are slow. And then you'd have reliable storage, because apparently you don't trust databases to be reliable either. So you've actually got this three-part architecture just within the database layer, which created a huge amount of complexity. And anyone who has actually tried to run a high uptime, high availability site, ops guys who are actually putting together these kinds of systems, that's a pretty hard thing to do. And I mean, still a lot of storage is sold, a lot of Oracle is sold in the middle, and a lot of people are putting coherence in front of their Oracle because Oracle's too slow and they're at their cache layer, right? So the internet companies said, you know what, we're going to collapse that part of the stack. Everything else stays the same. And I still need some Oracle, and I still need some relational systems. I've got some more legacy systems, but let's take that entire three-part stack and let's transition over to something simpler, direct attached storage. Because if you can't trust your database to be reliable, what the heck's it doing in there anyway? You really shouldn't have that second layer in the middle. And if your database is fast enough, why the heck am I using a cache anyway? Wouldn't you rather have one component instead of three? What are some of the providers? Well, of course, I'm going to talk about Aerospike as in-memory NoSQL, but I would be lying to say we're the only one. Right? In-memory NoSQL is now a broad area with a bunch of providers. MongoDB and Cassandra, I'm sure you're familiar with. I mentioned Redis earlier. Couchbase is also in the mix. So there's a bunch of providers with different strengths and weaknesses. At the app server level, I see a lot of Node. I'm sure you guys do too. It's not the fastest, but it has so much great tooling that running Node on the front edge is becoming more interesting. And Nginx. If you're running C these days and you're trying to run C++ on that front edge tier for a variety, for a variety of reasons, if you have that kind of heritage, Nginx, or even if you're running, say, Java underneath instead of Apache, I see a lot of people shifting to Nginx. Jetty is a really interesting architecture because it is asynchronous Java. So you'll see a lot of folks who have switched to, on that front application tier, using Scala and Jetty. So Scala is a lot terser, it's a lot more agile in terms of being able to actually code new applications, and it's also asynchronous. Asynchrony has really provided a lot of boost in terms of application tier because you don't have a lot of the threading problems that have always been an issue when trying to run very rapid application tiers. Research warehouse, I don't think I need to, there's not really any surprises there, but I will say one thing. My head is starting to shift a little bit about what Hadoop means in the modern world. I'm starting to think, and especially with the rise of Spark, super interesting technology, I'm sure a lot of you are interested in that. I was at Spark Summit, really interesting stuff they're doing. One of the worst problems on the backside of big data is having to move your data, ETL it. I've got those 15 databases, and I have to copy some part of it from here to there. That's usually the worst problem. Well, maybe HDFS is the answer. Maybe if we take those Hadoop stores, and instead of thinking them of as Hadoop, let's think about Hadoop as the processing engine, or possibly the entire ecosystem. If I've written my code in Hive, if I've written my code in Spark, if I've got some Hadoop jobs, and perhaps I even have HBase, some key value parts of things I just need to retrieve. All of those can go through HDFS, and that's probably a better way to think about the architecture on the backside, because there are so many different application analysis paradigms and different coding constructs you want to do. But let's keep the data in a minimal set, which probably means using HDFS as the storage layer, as opposed to thinking about it in any other way. So that's how I'm starting to think about the research warehouse problem. So when I go around and talk about the problems of modern big data, I recommend that people think about building this application-specific data layer, like I was talking about, that I learned from the Weibo guys. Key value store, I didn't talk about that as much, but really that's the key to sharding and operational databases. Any old school database will call that primary key. Don't do a join, just access by primary key, and do a certain amount of normalization, but don't get carried away. Right? That's what a database guy will almost always tell you is, where's your primary key access? How many joins are you doing? That's part of the analysis, and all of the in-memory solutions, in order to get scalability, are driven by primary key, i.e. key value access. That's how to make Cassandra go fast, it's how to make Mongo fast, it's how to make Couch fast. Even with Redis, it's sort of the only game in town you have to shard through. So key value really becomes one of the critical parts of building a practical front-edge database. Using memory NoSQL, yeah, but we'll talk about Flash in a minute. And so I recommend that people really take a hard look at what's in their front-edge in-memory store and how they're grooming it and managing it, and what part is actionable about it. Because if you think about Flash, most people, I talked to a fellow here earlier, he's like, oh, Flash, it's so expensive. Well, guess what? Compared to RAM, it's cheap. It's 10 times cheaper than RAM in a lot of cases. Now, some of the cloud guys, I have to warn you, if you're pricing Flash, they're not pricing Flash cheap. I think one of the offenders of this is SoftLayer. They're actually pricing their RAM, their Flash at the same exact price as RAM, because they kind of know that there's a lot of database guys out there who are, they've got over a barrel because they have to use Flash. They've actually driven up the price of Flash and driven down the price of RAM a bit. So depending on which cloud you're on, if you have access to either managed hosting, where Flash tends to be cheaper, and prices tend to be a bit more in line with the actual hardware price, but Flash can really be a way to either drive down your price, or you can think about it as driving up the amount of data you can have on the front edge of your big data application. And of course, on the far side, use open source. And the reason for that, I'll tell a little story. So ran into a fellow colleague from Novell, and back in the early 90s, Novell was an incredibly fast operating system, but it was impossible to program to. It had a non-preemptive kernel. It didn't do context switching. It had all these crazy rules. But if you knew how to write for NetWare OS, you could write incredibly fast code. So as an employee of Novell, I could go read the source code. I could also call up Drew Major and the guys in Superset and go, hey, guys, I've got a fault here, and I think you've got a bug in your code. They were really nice about it. But you had to have access to the code just to understand the operating system. And I think that's one of the biggest benefits of open source. It isn't just about getting things for free. What we find at Aerospike is people doing real work in real production, they will pay for quality. It's not about that. It's about being able to integrate your application, figure out how something works, not depend on the documentation, which is often faulty, right? Being able to go and read the source code is a way to quickly get your application working. And that's why I think it's one of the most important parts of this. So at Aerospike, what we did in order to solve these problems is we looked at a shared nothing design, because we knew clustering was a key part of the equation. We also knew that geographic replication, anyone who cares about uptime and cares about delivering a quality service, is in multiple data centers. So you have to have geographic replication. We baked that in. And we said, you know what, building out a sharding layer is a lot harder than it seems. Anyone who's built their own sharding layer knows that you start out very simple. You just say, oh look, I'll have a hash, and I'll break it into 13 shards, and I'll put 1, 2, 3, 4, 5, and I'll have 16 servers, and it'll be great. And then you start dealing with connection pooling and determining upstate of TCP connections. And then you have to start thinking about what your serializer is and cross-language serialization. All these client issues actually end up being a bigger and bigger part. And building a bulletproof sharding system ends up, you start in a week, you think you're done, and then it's a year later and you're still finding issues in your sharding code where you bring a server down and it doesn't fill the next part of the shard correctly, or you make a bug in your consistent hashing system. All kinds of things end up going wrong. So we built that into the top layer of Aerospike. What has allowed us to actually build a system that is 10 times faster than some of the other NoSQL guys? I think this would be of interest. I mean, a lot of you other people, you're all professional software engineers. You're also trying to build high-performance systems. So here's some of the things that I've learned in the last 5 years of building this. First of all, do key value. Make sure key value works really, really, really well, because that's what people who use a database expect to be fast. If key value isn't fast, if you're doing a query and you're going to touch a lot of rows, people expect that that's going to have a certain amount of either latency or unpredictability. But key value, you should know exactly what you're doing, exactly where that data is. Go get it, return it fast, get it right, and keep that code past fast. So we worked very hard on no hotspotting, on the hashing algorithms, the consistent hash that we use. Binary protocol, of course, is a key part of that. Once you saw the research on Memcache, their switch between binary and ASCII protocols, you know that that's a key engineering point, right? Code in C. We're a bunch of C guys. We don't really even trust C++. Once you have a library, you have something that could go wrong. You have one engineer who sees an interface and perhaps believes the header documentation and thinks it does one thing, when in fact, you've got some C++ polymorphism going on. In fact, it's calling a completely different function than you thought it was going to. So we find in our company that using C, it's a simpler language, which means that the code remains more comprehensible. There's less places that something can go off and do something squirrely than an engineer is thinking about. Multi-threading, direct device access. We found in our research that using MemMap and some of those paradigms, really nice and easy as a memory programmer, you kind of want to reach for MemMap. We found that in the Linux subsystem that was an incredible penalty. It was nearly a 4x penalty over just calling read and write if you try to use MemMap. So we don't use that. We use read and write. We also find that has benefits in terms of queuing theory, because you can cancel things. It's really hard to cancel a thread once it is sunk into a MemMap. There's just no interface for it. So even though MemMap should be faster, and it is in fact faster in some cases because you're going through less steps, what we have found in general is that using read and write and using async I/O are much shorter code paths within Linux. Memory allocation. Memory allocation is one of the banes of in-memory programming and programming in general. So this is part of our C pattern, is we don't anymore trust the CLib allocator in Linux. We found it to be spotty, it changes too much between versions, and one thing that happens, as this is a sophisticated audience, those of you know TC malloc? So people who use TC malloc thread cached malloc was a pattern created by Google that said, you know what, if you're allocating and freeing, you're probably on the same thread. Therefore, I can build a scalable allocator by essentially using thread local storage. It fails over, you know, if it wasn't allocated here and it was in fact allocated on a different thread, okay, I have to go look for it through all the threads, it's a little slower. Well, that's an anti-pattern for us. We only allocate memory in a case where we're going to move between threads. If we were going to be working on the same thread anyway, you know, use the stack. So therefore, the CLib allocator has changed a bit from, say, CLib 2.5 up into the CLib 13 pluses. It's become more and more like TC malloc and less correct for the kind of server applications that we have. So at this point, at some point we said, you know what? Just depending on malloc being shipped with the Linux kernel as part of CLib, we can't depend on it. It has too many different characteristics. We switched over to JE malloc, which is widely used in Facebook and other server environments. Our customer app Nexus uses it heavily. JE malloc has been really a big change for us in terms of reducing fragmentation. Also because JE malloc allows you to use memory pools. And pooling your allocation when you have application-specific knowledge about those allocations is the best way to fight fragmentation, which will often give you 2x better RAM usage. So that's been another part of what we do. It's been a good one. We found that compared to, say, a Cassandra, we found that the Dynamo path, Dynamo paper, not Dynamo DB, that says, you know what, in order to build large clusters, you just have to give up consistency. What we said was, you know, that is true. When you get up into 500 node, 1,000 node, 2,000 node clusters, Cassandra is absolutely right. The Dynamo paper is brilliant in that way. However, if you can make your database 10 times faster, what we have is we have customers running all of North American advertising, those 3 million transactions per second, on a 12-node cluster, with a lot of overhead, if you can make it go fast. How do you do that? You still have to use mastering. So a shared nothing environment, where from an operational perspective there is no master, it has to be that way from an operational perspective. You have to be able to kill any node. However, from a database perspective, on a row-by-row basis, having a master and replicas where you know where the data is and you know how to commit it, as opposed to distributed consensus, really becomes a win. And let me talk a little bit about cap theorem. Those of you who did not go and read Eric Brewer's article 8 weeks ago in InfoQ, go read it if you care about cap theorem, because he really clarified for me and I think for a lot of folks what he meant when he was talking cap theorem. And what he said was, you know what, if you're in a distributed system, you need P, because you can partition. Okay, so, and the world is all distributed systems now. There are no single node databases, or if there are, you know, go use them. That's fine. But this world is all P is a given. So now the only question is, when you have a partition, you have two choices. Do you break down nodes in order to maintain consistency, or do you keep nodes up and allow reads and writes that are going to be inconsistent because there's a network partition? To me, that's a much easier way to think about the cap theorem. I've just got a policy choice. Do I bring down nodes, or do I allow availability by keeping nodes up in the case of a partition? Well, it turns out the kind of architecture we have in Aerospike, we can do both of them. You can configure the system to either bring down nodes or keep up nodes and later synchronize your consistency problems. So it's a nice choice. You don't really have, it's not really, you know, you can have, so you can't have a AC system, et cetera, et cetera. So it's a much nicer, cleaner way of thinking about it. Another thing we learned is clients are hard. We under-resourced our client group. We thought, well, we're going to be a bunch of database guys. The database is the important part. Well, it turns out that making fast clients, if you don't have a fast client, as far as the API user is concerned, you don't really have a fast database. And you have to sweat the details in every single language. We have to learn about C#'s memory allocator. We have to learn about the Java serializer. We have to learn about all of these different things in every single language in order to really create a great client experience. Second of all, as much as I talked about key value, you still need to do aggregations and you still need to do queries, and you need to do them safely. There are still cases every once in a while in many different use cases where you have to have secondary indexes. You have to look up my email address. Just because those are less predictable and don't form the lion's share of your transactions doesn't mean you can slack off and not do them and just have a key value system. 7, we are fighting at Aerospike. The biggest problem in performance right now is network interrupts. That's our biggest issue with the Linux kernel. We've kind of nailed storage between, now being on the 4th generation SSDs from people like Intel and Samsung and Micron. Great work being done in storage. Storage is kind of a done deal. Now we're fighting network interrupts. And we're not the only people to say this. There's a lot of work that happens in the Linux kernel around the 3.6 version in order to revitalize some old network interrupt code. We're still fighting, and that's probably the biggest problem we have right now. We also found large data types. So an interesting issue here is, so for example, financial services. You have some users that have done 1 million trades a year, and some users that have only done 1. So you can't simply think of a row as a single row in a database with fixed schema anymore. You have to think about it more in that Mongo document-oriented way, where a row, a user, that's sort of how I'm partitioning up my operations. I might have very, very rich structures underneath an individual key. So they could be multiple megabytes. It could even be a gigabyte of historical trade data. That's absolutely necessary. Last point, UDFs. This is an old database trick. In some ways, it's an answer to those network interrupt problems. The network is starting to become the new bottleneck now that we're past storage being the bottleneck and into in-memory. Well, so the answer is always, as always, is you push your compute to your data. It's a layer violation. Sometimes it's a bad idea. Maybe you should keep your compute back in your application tier, like I said. But then occasionally there's this itch to push some of that compute down into the database. So we've allowed that in Aerospike. We're sort of monitoring how that goes in terms of creating a reliable system where there's user-defined functions in the database, but it's part of our bag of tricks. So I'm going to skip through a little bit. One thing that we found in terms of being a NoSQL database, my new quip is we're a NoSQL database, or not only NoSQL database. We started out saying it's a polyglot world. Even 10 years ago, it was clear that polyglotism in languages, using lists and maps, whether you want to use Scala, you want to use Spark, you want to use Ruby, the database should support everything. Well, guess what? There's nothing wrong with SQL. There was a big reaction against SQL, partially due to more agile systems and schema modification. Really that, in my opinion, was more about rotational disks. Rotational disks demanded having pre-partitioned and pre-sized rows. And that's one of the great benefits of in-memory. However, that doesn't say anything about SQL being bad. It's more about the implementations of the time. So what we found is with SQL, we can actually use MapReduce style and filtering techniques to actually do the kinds of queries that you would normally do in SQL in parallel by basically breaking SQL up into filtered MapReduce. And we have some interesting patents on these secondary indexes combined with MapReduce patterns. But we found that essentially we can answer all of the needs of SQL within this kind of very parallel environment. So I'm going to talk a little bit about Flash for a minute, because this is one of the key technologies. Some of the keys to working with Flash efficiently. Flash has a couple of different important differences from the old rotational disks. The first one is it's more parallel. You need to load these devices up with deeper queue depths, just due to the nature of the hardware. It's not like rotational disks. You've got to move the head, you read once, then you move it somewhere else, and read a second time. You can't do 2 operations at the same time. Now, the deeper your queue in a rotational system, you can do more elevatoring, and you do get a boost. But with Flash, essentially it's free to get more parallel. These devices perform best at queue depths of usually between 128 and 512 parallel outstanding IOs, and they don't block between each other. Each device usually has between 10 and 30 different coprocessors doing IOs and dealing with storage behind it. So if you can't get that level of parallelism, you're wasting part of your SSDs. And this is one of the reasons that, in my opinion, a lot of those old relational systems, you put SSDs, they get about 2 times faster. And that's because streaming speed of SSDs is about 2 times what the streaming speed of a rotational disk is. But the number of IOPS are 100 times better. Instead of 200 IOPS per device, you're getting actually now into the 200,000 range, 1,000 times better. So if you can use this level of parallelism at your SSD layer, you'll see a dramatic increase in speed. The second thing about SSDs is you have to avoid the file system, because those file systems are typically not at flash optimized. And second of all, the indexing systems with file systems, okay, so you're not updating a time every time, but you do have a lot of hierarchy within those systems that's unnecessary. If you're a database, you already have an index. I should know where to go. If I'm on top of a file system that's creating yet another layer of indexing, I'm just wasting time and creating complexity. So we found those were a couple of the keys. The next thing we found is the incredible motion and improvements that have happened in Flash in the last, has it only been 4 or 5 years since the introduction by Intel of the X25, the first mass market SSD. So what we found is first generation, the X25 out of Intel, second generation, the 300 series, 300, 500, 700, 900 series, third generation currently shipping the S3700, S3500. And now we're into the fourth generation. We've seen samples, I'm sure other people have also. So we're into fourth generation over this period of time, and drives react differently. So what we had to do is we had to say, there's no good benchmark out there, because when you're writing to a drive and reading from the drive at the same time, different devices, different controllers all react differently. Even different lithography between how MLC, TLC, and SLC reacts are all different as well. So if I'm going to tell someone as Aerospike, hey, you need 1 million IOPS, go buy this device, I better go measure this stuff. And the worst problem with SSDs is they have a little garbage collector in them. Right? That's how you really have to think about SSDs, is there is a garbage collector in it. And garbage collectors are the death when it comes to predictable performance. We know that from Java use, right? So the fact that there is a garbage collector, essentially different drives have higher quality garbage collectors, whether they're doing incremental, whether they're doing pause the world, et cetera, et cetera. So we created a tool called ACT, it's open source, and it covers a lot of the common key value use cases. You can set the parameters at different points. But this has allowed us to check into different flash devices and work with manufacturers for low latency cases. A lot of the flash guys have been focusing on the Hadoop big data market, which is not IOP focused, right? So they focus a lot on streaming and throughput, and not as much on the kind of internet, go get this key value use case, which caused us to create this benchmark. So know your drives, go look at them. Another great thing about Flash right now is the level of Flash support within all the clouds has improved greatly. So we saw a lot of great new Flash offerings out of Amazon over the last year. Google has gone semi-public with a lot of their new offerings, which is great. I'm really looking forward to it, what they're putting out there. The managed hosting guys have had Flash for years, so people like the Rackspace, SoftLayer of the world, they've had a lot of good Flash offerings over time. So the good news is, in every cloud today, you have the ability to access Flash or the ability to use RAM for different data sets. Third point, a lot of people talk to me about write durability of Flash. We have found it is not a problem. So you have to go through the math, right? But part of the, I would say, second generation of SSDs, even with MLC, and the way that they measure this is in drive writes per day. That's something that Intel cooked up. If you're going to rewrite every single byte on the device, how many times a day can you do that and have the drive last for 5 years? So Intel specs a lot of this part now, 5 drive writes per day. There's some 1 drive write per day stuff. But what happens practically is if you're writing that much to the drive, it's fragmenting, its garbage collector is going off, and it's really, really hard to read it. So even though you can burn through one of these drives in 20 days, if you're writing to it that hard, you're not reading from it. So when we actually do the math and go through for a customer POC, we have never found a case that an MLC drive was not appropriate. MLC is appropriate for a vast majority of these kind of enterprise workloads, simply because of the fact that if you're reading from it, if you're writing to it, you need to read from it. If you're going to be write-only, you probably should be using a rotational drive anyway. You're probably writing without overwrites, or maybe it's even appropriate for you to consider RAM, which doesn't have these. So a lot of good choices there. Let me tell you a little bit, since we're here at Samsung, I've got my Samsung logo up there. I've talked a lot to what's happening with these different manufacturers about what their roadmaps are over the next couple of years. We're about to hit an amazing change in density. Now, unfortunately, Flash is not going to get any faster over the next few years from everyone I talk to, but it is going to get more dense. Right now, the densities that I'm seeing deployed in my customer base are approximately 5 to 10 terabytes raw per 2U server in a data center environment. That's 5 to 10 per 2U. What we're going to see starting early next year is 50 terabytes per 1U. Massive increase in density at no increase in price. They're just using new designs and layouts within data center environments. They're using lower power devices. They're simply using next generation devices as lithography changes, as Samsung created 3D flash, wonderful device, much higher density. Regrettably, MLC, the latency to chip on reads is going to stay at between 70 to 90 microseconds. So there's still a place for RAM. RAM prices are coming down. Prices on flash, enterprise flash, look like they're going to stay roughly the same. Right now they're probably at $2.50 a gig, $2.50 a gig. They're going to trend down a little bit over the next couple of years. We're going to come down to maybe $1 a gig. Maybe we're going to hit 75 cents a gig. It's rumored that people like Apple are getting even a better price than that. Nobody's getting below 50 cents a gig. And that's probably not going to change, honestly, over the next 2 or 3 years. But density will increase. The ability to pick up a 50 terabyte, 100 terabyte array and stick it in just a couple of views, for those of you still in a data center and not using cloud, can provide interesting opportunities for companies doing real-time big data. So, these advertising companies, they're keeping cookie pools of 10 to 20 terabytes. Well, I mean, that's going to be nothing in a couple of years. So those of you in big data, think about putting more data on that front side tier. Because I'm telling you, with Flash, the densities are going up, and your opportunities for doing algorithms that take more data on that front side tier is going up. Pricing, let me just speak for a minute about wide SATA. There's a lot of manufacturers out there talking about PCIe and NVMe. We have found that that's a little bit of a red herring, which I hate to say at Samsung because they're big NVMe proponents. But it turns out the SATA devices, these kind of use cases are not bandwidth bound, they're IOP bound. And the SATA drivers are very good in terms of IOPS. So at modest bandwidths, you're really driving IOPS, you're driving a number of transactions in back-end co-processors. And SATA is actually still a very reasonable choice. We will probably go beyond what SATA can provide, but we're actually not there yet. Some of my customers are doing things like 250 to 300,000 IOPS per server, and they're doing it with SATA, using these kind of wide SATA deployments. So that's 200,000, 300,000 per server in a clustered environment over SATA. So in my opinion, NVMe and PCIe is still a coming thing. It's nice, but for these transactional workloads, not actually required yet. Let me show you some interesting data that we collected over the last week. So, it's all nice to talk about in data center work, but the fact is all of us are in the cloud these days. So we started looking at a different problem, which is if we say at Aerospike that we're more efficient, what does that mean in the cloud? It doesn't mean the number of servers. It doesn't mean the number of IOPS. Because if you want to provision another server, you press a button, you get another server. Who cares about the IOPS per server? What you really want to know is the transactions per buck. If I buy a $4 server or a $1.25 servers, how many transactions do I get out of that? So we did a little attempt to figure out in Amazon EC2 what the different performance is on Aerospike, some of the different instances, and trying to find the price performance leaders among the different instance types in Amazon's. So we found one interesting thing was that some of these machines, the C38XLs and the R38XLs, are actually capable of 1 million transactions per second using Aerospike. Single instance, that fast. So kudos to Amazon for one thing, because the improvements they did in the hypervisor in the C3 and R3s are really exceptional. So the price per transaction is actually linear across the 2XL, 4XL, 8XL family of both the C3s and the R4s. But really, compared to the old stuff, we're just in a completely different ballpark here. So really liking some of these changes in Amazon. So here's some finer grained results. What we found in some instances is Amazon does have some network limits in terms of packets per second. It's a way for them to keep their network infrastructure sane and not have the kind of congestion that they've been known for over time. So you kind of have to know which of the devices are actually limited in terms of packets per second and which ones aren't. Just because you have a 10 gig instance doesn't mean you can push as many packets per second as you might want. You might think, well, if I've got 10 gig, I can get more packets through. Not necessarily so. So we've gone through and done all of this. This raw data will be published as part of an Amazon blog post by Amazon in about a week. So I'm giving you a little preview. I found this to be even more interesting, which was, think about it in terms of manageability. If I want 500,000, if I want 250,000 or 1 million transactions per second, how many nodes do I need of different sizes? So we've gone through that exercise with Aerospike also. What this should tell you is, even in the cloud environments, these are all RAM numbers, by the way. We're still working on our Amazon SSD numbers. Like I said, this was a little bit of a preview. Getting up to 1 million transactions per second in Amazon, well, look, those R3 2XLs are really doing pretty well there. We'll need a couple of those, add up a couple of those to get to these kinds of performance levels. And I especially like this graph because it shows the distinction in terms of really what the bottom line which is dollars per month that you're spending for a given TPS level. Again, this is in memory, using I think ephemeral rotational for a backing store for persistence. I think we also did it with EBS, just basically screening the writes for EBS, same kind of results. But you see a really different curve there between the old M series and the 3 series. On the other hand, the 3XLs, since they are so much bigger, down in the bottom end, you've got a different split here. But then the R3s start taking over. So in general, these R3 machines are really on a completely different curve than some of the older M machines. So this is some of the stuff we're doing in Aerospike to try to figure out and predict, for those of you with big data, how much money you have to spend to get a certain amount of throughput. Because that's part of your algorithm, right? Part of your algorithm says, well, do I need to do this transaction? Can I use 3 transactions to do this piece of analysis or just 1? If I know what the cost of doing a transaction is, I can actually figure out what kind of algorithm works best in terms of this front and side space. So anyway, I was talking about open source a little bit. Aerospike recently made the journey to open source and some of the benefits of it. So what this means is you can go up to GitHub right now, Aerospike/Aerospike-server, or just go to our site and you can actually see our source code, see what we're doing, all of these reasons why we've actually created a high-performance database. They're all out there in the open. So all these performance numbers, you can try them all out yourself. They're all on Amazon. So if you think we're lying through some of these numbers or you can't reproduce them yourself, give us a call. We've reproduced them. We know that they can be done, and we want to engage in that dialogue. And open source is part of that. So that's the end of what I have to say here. I think this new architecture of using application servers and an in-memory data tier on the front side really provides a lot of new opportunities. The advertising community has used it to great extent over the last 5 years. We're seeing it sink into more and more enterprises and create some really interesting opportunities on that front side tier. So, any questions? Yes, in the back.
Yeah, well, actually, so it looks like tape gonna be next spinning disk, and SSD flash gonna be next next tape, and next
Well, I mean,
gonna be next spinning disk, and what do you think about what's next in memory?
I don't know. I'm not a hardware guy. I'm a software guy. I think rotational still has 5 years, honestly. It increases in density. We're not seeing the kind of price decreases yet that allow us to really forecast the end of rotational disk. If you want to put together a lot of petabytes, that's why you want to use HDFS. You still need streaming, and that's going to be with us for a while. The cost of rotational is still around, what, 5 cents? And flash, even the cheapest flash, is at 50 cents to $2. So rotational will have a place. It'll have a place for a long time. All of the Hadoop knowledge we have built up will still serve us in that back end for at least another 5 to 10 years. Yes?
Thanks for a very good talk. I need to learn something that I'm going to ask a couple of basic questions. You talk about using flash so extensively. It does solve a lot of read-oriented, but it doesn't solve the right. And you said you were also at the Spark Summit. How do you view RDD? What can you do different?
Okay, so the first question is, talk a little bit about flash and writes. So what we had to do in optimizing Aerospike was doing update in place is still very tricky for a lot of flash devices. I found that the newest, very newest controllers, I went up to Intel and talked to their controller designers, they now think that they've cracked the code in terms of being able to do 4K updates efficiently and not create a lot of garbage collection. My data is still out. I haven't actually verified this yet. But we can start doing 4K writes at a pretty high rate. What we did at Aerospike was we said it's important, at least in the older generations, to write in much larger chunks. And with that, you can still get a high level of throughput. So we write on 128K boundaries and undergo a certain amount of queuing delay when we're doing those kinds of writes. So we've been able to get very high write rates. In advertising, usually, we see a lot of cases where it's 50-50. I think about advertising like trying to drive a finite state automaton, where we, humans, are all we're the devices you're driving. You think about the marketing funnel. Do I know there's a problem? Okay, if I've advertised at the person enough, we now know there's a problem. Now I can move to the next state. Now I can move to the next state. So in advertising, if I show you, first I have to do a read to decide what to show you, and then I just showed you something, I have to do a write. So we see a lot of very 50-50 workloads, and Flash can be used in cases where you need up to 50-50. When you're driving up past 90%, Flash is not appropriate. And that was sort of the case I was saying, where at those points you're going to burn out your Flash, you're going to be down in a 1 month to 2 month burnout cycle. But that's really rare. As long as you're up in the 50-50 case, you're going to be in pretty good shape on Flash. Or you might have to switch to SLC Flash. Second question about it was, remind me?
RDDs.
RDDs. Really great technology. Super excited about it. We're talking to the Spark guys. So the idea there, for those of you, let me just recap a little bit. What the Spark insight is to say, you know what? When you break apart a query you're breaking it into a directed acyclic graph, a DAG, and then as data comes in, you can keep pointers and do partial recompute based on data that comes in. So if I have an update and I store enough of the DAG that was used to compute the result, I can do the minimum possible recompute of even a very complex computation, which is a really snazzy idea that I'm very excited about as well. What they do is they tend to keep that DAG and tend to keep the RDD in pure RAM. But they also have a storage system called Tachyon. I think there's a meetup tomorrow from the Tachyon guys. And I'm starting to talk to them too, because now that we're open source, this might be a better technology, or at least a complementary technology in some cases, to keeping the kind of shared RDP state that is used in Tachyon. So very excited about it. I'm talking to the Spark guys about it. We're storage guys, they're query guys. We'll see if we get along. Maybe it'll happen.
Good answer.
Any other questions? Yes.
You mentioned about the two different architectures, especially in the new architecture, the application server was a really neat comparison. And you mentioned three vendors, yourself, BDG, and Cassandra. Would you mind elaborate? What's the differences are in comparing the three options, whether it's price or the number of deployments? And
Sure. So a little bit of comparison about some of the. What's that? Yes, repeating the question. So the question is, talk a little bit about some of the differences between the in-memory NoSQL providers. So the way that I see MongoDB, I'm sure a lot of you have opinions about MongoDB, it's widely used. My opinion about MongoDB is informed by the following. So one of our investors is NEA, one of the large venture firms. They also invested in MongoDB. And so they see us as complementary technologies, not conflicting technologies. Mongo is great for ease of use. So if you really want to get started fast, you're using JSON, and you can even do joins in Mongo, right? You can do text searches, you can do all kinds of things. You can also do key value and follow the kinds of paradigm that I was talking about for building a shardable, scalable in-memory system. But in my opinion, that's not their strength. Their strength is really the ease of use that comes with a very broad set of programming primitives. So they've given that kind of capability, and it makes it very easy to use. But unfortunately, in my opinion, people fall into the same kind of relational-oriented thinking, where they're still doing joins, they're still doing large-scale queries, and those are inherently non-scalable. So it's kind of interesting historically, I think. We'll see what ends up happening in the next few years. But they've given application developers all that they want. The problem is they've given them some queries that are non-scalable. So is that a good thing? Yes, it's because it gave them an ease of use. However, now they're in a situation where they've given them tools that don't scale. So it's a double-edged tool. A lot of people like it, a lot of people use it, but they've capitalized on ease of use. as opposed to performance and scale. Compared to Cassandra, Cassandra really focuses on large clusters. So they can handle cases where, the paradox of distributed systems is the larger the cluster, the more failures per unit time, because you have that many components that possibly fail. So Cassandra is focused on the problem of what if I have 1,000 nodes? What if I have 2,000 nodes? What if I have a 5,000 node cluster? And that's where you say, you know what, you can never have consistent writes because you don't know where there's a failure. You just have to take a write somewhere and then synchronize it all up later. Let's just give up on consistency, which in fact is the right answer when you have large-scale clusters. So very interesting choice of technology, and I think a correct one for a particular set of problems. The people I know who use Cassandra and use it successfully tend to use it for time series analysis. So it tends to be almost, in its best use, a little more of an analytics tool than properly for key value. What we find is when people are sticking to strict key value, that's a case where Aerospike is the appropriate technology. So we replace Cassandra only in cases where it was a real key value use case, as opposed to that. The second problem, in my opinion, with Cassandra is they focused on rotational disk. It was just slightly an older technology. So they have this intermediate memory pool, it creates an extra buffer copy, they then do a finalized merge sort out to rotational disk, which is absolutely the right algorithm when you're using rotational disk. However, and so for people who will need rotational disk sizes, who are building, at this point, 200 tera front-edge clusters, Cassandra might in fact be an appropriate choice. However, with the increase in Flash, I think that that'll become less appropriate of a choice. And we already saw DataStax come out with their memory version. Unfortunately, I think it's an enterprise version, so we haven't tried it out yet. So I think the writing's on the wall there, where they sort of see that this in-memory case is different, and they're trying to change that. Of course, the other issue is Java. Those of us who've used Java and tried to tune Java know that it's troublesome having that in the technology stack. Redis, I was mentioning also. Redis, really great tool, amazing speed, kind of a pain to operationalize because it's single-threaded, single-core. So the best practice on Redis is if you've got a 16-core processor, you're running 16 different Redis instances, which means across your entire system you've got this huge number of Redis processes, and you have to build a fairly complex sharding system. The guys at Redis, they're all essentially unpaid. Some of them are paid by the VMware guys. And they tried to put sharding and clustering within their system. Unfortunately, they couldn't. And I'm not surprised. It's a super hard problem to try to add a distributed system later when it wasn't designed in from the beginning. And so hard problem. They didn't really get there. Yeah, it kind of works. I know one person using it in production. They're not very happy. So instead, you end up creating your own shard layers. And there are some shard layers out there for Redis that work pretty well. Does anyone else have some favorite NoSQL databases or databases I should compare to in this space?
Gemfire.
Gemfire, wonderful product. I love those guys. I've met them before. They have focused on, what I like about them is I think that they are the dark horse in terms of generating revenue off of NoSQL. They were NoSQL much earlier than anything else. They never really optimized for SSDs. That's one thing about them. And they are sort of tightly coupled in with some of the VMware infrastructure, which is a plus and a minus in terms of using RAM. Their internal architecture, though, is really sweet, and they seem to have fairly high performance, and very seriously enterprise. So for pure enterprise customers, pretty interesting product. We don't come up against it that directly, so I can't be more specific than that. Couchbase? So they're probably the closest to Aerospike in terms of technology. They're multi-threaded. They started out with an Erlang base, and then they replaced some of that with C, and they had some of the memcache capabilities. So we tend to find RAM-based. We've done some optimizations in the last few months. We're now beating them by a factor of 2 out of RAM. And we tend to hear a lot of issues with cluster formation and rebalancing when using Couchbase. And they claim a lot about SSD optimizations. However, that's where we tend to beat them head-to-head when we're talking to customers, is when it comes to SSD optimizations and performance. But interesting products have been open source for a while. A lot of people like them. Anyone else? Sorry? VoltDB. Really VoltDB, interesting early player in-memory analytics, really focused on analytics, not really a player in operational databases. Never seemed to really generate the level of performance, Java-based. We sort of took a page from them in terms of the way we do analytics, in terms of user-defined functions. So, Stonebreaker's been around for a million years, and most of his ideas are correct. So doing push down of these kinds of query layers using UPS, fabulous idea. But he's on to a new company at this point, and we've even replaced some VoltDB in terms of analytics.
But they have a newer generation called S store. I'm not sure whether it's topic.
Yes?
Most of their examples are key value stores, sets of basis.
Yes.
There's a lot of, so I'm kind of learning a little bit more in terms of graphing databases, since
Yes.
you want to rank and prioritize and recommend and build those type of stores. How does that play or affect your architecture of what you perceive of
Very interesting question about graph databases. Early player Neo4j, of course, created some interesting interfaces. Unfortunately, they're having problems building a scale-out architecture. So as long as you keep it single server, I think they have a nice enough API. Not having used the API myself, I hear some people complain about it. I was in OSCON last week, and there's a fellow I met who founded his own graph database company. So it seems like there's like 4 or 5 graph databases coming out of the hills. It's an interesting paradigm. I think people should adopt graph thinking more and more. What I see from our perspective is people sort of hand code graph use cases over Aerospike all the time. They put a list, and that there's like a list of user IDs, and then they go fetch that list, and then they do a batch get, and then they sort of get the next generation. So that's kind of clumsy, honestly. And it would be nicer to have graph-oriented APIs. So I guess I think about graph more as an API set like SQL that really every database will end up supporting
more
over
of a
time.
computing engine and analytics side, but not in terms of data set?
Well, no, because you do want graph use on the operational side. There are cases where it's completely reasonable to do graph-style query and use graph-style APIs. So, in-memory and Flash really get you that because you do have very random access patterns when using graph-oriented indexes. So I think we'll see a lot of improvements just in the next couple of years. Like I said, I've met a couple of people doing new startups in that area. And we'll eventually see more of graph APIs converging with some of the other NoSQL players. Right now, it's sort of off to the side. I think we'll see it coming in a bit more.
Does Spark have a graph? Does Spark have a graph?
Does Spark have a graph database? I do that?
It's not a database.
No, it's
Yeah, they have a graph analytics tool, right, exactly, which is kind of similar to their same machine learning tool. There's a lot of great things you can overlay with Spark. Yes?
So Aerospike is a data solution provider, not only for database, but also you can position as a storage company. How much of your efforts is being divided between off-cloud and on-cloud?
So the question is, how much time do we spend on cloud versus off-cloud? I would say we find that most of our efforts in terms of creating new indexes and creating new clients, we're just releasing a Go client. We've just pre-released it to 4 or 5 people. Any of you rabid Go fans who want to try to use us with Go, come see me afterwards. So I would say a majority of our time is not cloud or non-cloud specific. Probably 75% of our time spans all uses. I would say at this point maybe then it's half and half between cloud and on-prem in terms of optimization and working with customers.
Yes, so those data sets based on-premise, potentially they can go either public cloud or private cloud.
And so at Aerospike, that's one thing we tell people is, do you really want to get in bed with Amazon all the time? Wouldn't you rather use a database that you can take with you from place to place? I have one story about a particular customer, I think it was Exelate, who had a data center provider, a managed hosting provider in Texas as part of their geographic distribution. And those guys started doing a bad job. Some of their key employees left. They were able to hire another data center provider, put them in the replication ring, get the data transferred over within about 2 weeks, and switch provider, managed hosting provider, from one to another within literally a couple of weeks, which for those of you who have actually changed data center providers, it never takes a couple of weeks. So creating sort of multi-cloud environments, I think is pretty important. And I think that's really one of the benefits of the database layer is creating, whether it be OpenStack. I think OpenStack is another great effort in the area of creating basically multiple hardware provider interfaces, so we all don't get locked into one PaaS provider. That'll be a coming thing over the next few years. Yes?
Would you be able to comment on a lot of companies like
Sure. So the question is why companies like Twitter moved away from Cassandra? Facebook, of course, is one of the early creators of Cassandra, used it for one specific use case, which was their message inbox. And I don't know exactly what caused them to stop using it. That was actually many years ago. They sort of went back to using the sharded MySQL system that really the rest of their infrastructure was based on. So they sort of had an introductory, project of a bunch of guys who had the philosophy of creating something based on the Dynamo paper, but then they ended up sort of just going back to their standard infrastructure. Within Twitter, I think they found something similar, right? So they created the Manhattan project. They have their own internal key value store system. They open sourced something new recently. They seem to like open sourcing their key value systems. But they found that their in-house efforts were more usually CPU efficient. So one of the big problems with Cassandra that I find is the CPU inefficiency. And once you start working at a certain scale, you sort of go, wait a minute, I'm only getting 10 to 20,000 IOPS just because I'm CPU bound? That's crazy. And you start thinking about being able to get a higher level of performance. And an internal team can do this. I mean, Twitter can hire the kind of people that are capable of doing the levels of optimization working in C that will get you the higher level of performance, and they've proved it. So that's my personal opinion. Yes?
I have a question about what is your architecture. I'm not quite sure. Actually you said that it's a master slave kind of a management or peer-to-peer. And then the other question is your user case is the largest cluster. How large it is? And how about the other things? Do you have any global kind of data center to data center kind of use case?
So the question is, first of all, Aerospike's architecture. I'd be happy to talk to you about that offline because it's kind of a hybrid model. Okay. So I went through quickly, saying we have sort of this distributed master algorithm. Right. So it's probably, we can talk about it later. The cross data center replication that we do absolutely have worldwide replicated data sets among our customer base. Any other questions? Yes?
Basically, summarize why you think the master the sharded MySQL masters.
Why sharded MySQL with masters is a better architecture?
Yeah, rather than
Okay, sure. So the issue is, this is a question of sort of what you were asking about how distributed transactions work. So the Dynamo model, Dynamo paper that Cassandra, React, and DynamoDB probably internally use says, you know what, we'll take the application to specify a read factor, R factor, and a W factor. And that'll allow you to, as part of the synchronous processing, know the number of writes that you're doing, and thus allow you to figure out what be able to do things like consistent reads and writes, which is a pretty good idea. The flaw that I found in that is that sometimes there are more copies of data in the cluster than you might know about as a client. You might think there are only 3 copies, but what if a new server has just come online and for a short period of time before it's rebalanced there are 4 copies? So it's very hard for a client, a piece of client code that doesn't understand exactly where all of the data is to make consistency choices. So I think that the way that Aerospike, Gemfire, and MongoDB, and also Coherence uses the same models we do. What we say is, you know what? The client should just specify the policy. Do I want a consistent write, or fire and forget, or give me a policy? The cluster knows enough about where the data is, where the masters are there unreconciled pieces of the data, et cetera, to make the correct choices in terms of the transactional commit. Let the cluster apply the policy choice as opposed to having in the client an R factor and a W factor, which is proxy for a policy. So by having the policy in the decision in cluster, the cluster can know how many copies are there because there's a master, which at that time it's a distributed master. It's not a single point of failure, right? You have to make sure that it's a distributed master system with no single point of failure. If you can do that, it's actually more appropriate, higher speed and higher reliability to use that kind of technology that Mongo, us, Coherence, and a couple of other systems use, as opposed to the kind of distributed commit system that can lead to unintended results in particular corner cases.
So
We probably should take any further detailed questions offline. It's a pretty deep question and a very interesting area of research. Yes.
So in summary, like in the cap theory, like are you guys making the trade as kind of consistent, relax on consistent kind of approach to almost set of libraries?
So when I was talking about the cap theorem, I think what Brewer, when he stated it more clearly the second time around, he said you only have two choices, AP and CP. And all that means is, do I shut down servers when I detect a partition? That's the only choice that you have. And you can do both. You can have that as a policy decision that you make one way one time, another way another time. Different parts of your data you can make unavailable. Different parts of your data you can keep available if you can detect a partition. So the Aerospike architecture and other similar architectures are capable of making that choice on a data set by data set basis. That's a much simpler way to think of the cap theorem than pick 2 out of 3, et cetera, et cetera. So that's the only real choice the cap theorem provides. Shut down servers or keep them all up and generate inconsistencies. That's a policy choice. You can do one or the other at different times. You can have policy knobs for it based on data sets, et cetera.
What's the price to pay for that? What's the price to pay for the to have both?
What's the price to pay for both? They're really, well, it's a coding complexity.
That's your side.
That's my problem. Or those of us in the database community. Yes. One more question. We said. Yes.
Do you have like secondary index
We have limited secondary index capabilities. So there are, like I said, you do need to do, sometimes you need to do a secondary index lookup. It's not a scalable way to go about your business, but sometimes you need to do it. Sometimes you want to run a little BI run on your hot data. So we have some of those capabilities in Aerospike. They're not as advanced as in MongoDB. That's one of the shortcomings of Aerospike. However, we're adding new indexing all the time. So hopefully, my purpose for being here, besides sharing some of my experience in this field, is Aerospike really works. It's freely available. Just go and download it and try it. So people say, hey, Brian, you really sound like you know what you're doing. I really like the technology. And I just say, have you tried Aerospike? You're using Cassandra, you're using Redis, some Mongo use cases. Aerospike is simply a better product, and it's free. So you can download it and try it. Let me know how you like it. So.